Bismillahirrahmanirrahim, and welcome to lecture number 20 for basic engineering mechanics. In this lecture we will continue our discussion about equilibrium for a rigid body, and we will discuss how we draw the free body diagrams and represent the support reactions in coplanar or two-dimensional system. So as we discussed earlier, anytime we have a support, we have to replace that support by a reactive force, and depending on the support, the reactive force could consist of 1, 2 or 3 unknowns, which we discussed last time. Okay, so here we look at some other examples, practical examples. Here the support is due to a string or a cable, and we saw that the cable can only provide a tension along the direction of the cable. So in this case the support reaction would be because of a force which is in the direction of the cable. So we would only have one unknown corresponding to this support. In this second example we have this pin support, and so we have a pin here, and because of the pin, the translation motion both in x and y is not possible, which means that this pin has to be replaced with two support forces, one in the x direction and the other one in the y direction. So we would have two unknowns. Similar case, the third example, here we have a rocker, and as we saw before, this rocker only stops translation in the negative y direction, so that is why this would provide an upward force in the vertical direction, which corresponds to only one unknown. Here we have a welded beam, and as we discussed earlier, a welded beam stops both translation and rotation. So in this case both the translation in x and y are restricted, and the rotation along the z-axis is also restricted. So we would replace the support with two forces and one couple moment, and so that is why this support would give us three unknown reactive, two forces and one couple moment. Okay, so the main topic for today is about equilibrium in two dimensions. So last time we saw that the requirement for equilibrium was sum of all the forces is equal to 0 and sum of all the moments at any point O are equal to 0. But these are vector equations, and in two dimensions we would translate these vector equations into these three scalar equations, because we know that anytime we have all the forces in two dimensions, then the moments are always perpendicular to those forces. So the moment can just be treated as a scalar, which can either be negative if it is clockwise and positive if it is counterclockwise, and the forces only have two components, their x component and the y component, and sum of all the x component of the forces have to be equal to 0, and sum of all the y components of the forces have to be equal to 0. Notice that these three equations are not vector equations, rather they are scalar equations. Here these two equations are vector equations, and if we were to use Cartesian coordinates to write these equations, these would translate into 6 simultaneous equations. But in this case we have, in the case of two-dimensional system, we have 3 simultaneous equations. Okay, so notice that in two dimensions the requirement for equilibrium, the equations of equilibrium are not unique, in the sense that if all these three equations are satisfied, sum of all the forces in x are equal to 0, sum of all the forces in y are equal to 0, and moments at any point are equal to 0, we would have equilibrium. Even if we have these other three equations, that sum of all the forces in x are equal to 0 and sum of all the moments at point A are equal to 0, and sum of all the moments at point B are equal to 0. If the sum of all the moments are 0 at two independent points which are not parallel to the y-axis, and sum of all the forces in x are equal to 0, even then we would have, these are sufficient conditions for equilibrium. And we also have a third alternative set for equilibrium equations. So if sum of all the moments at three different points is equal to 0, and all these 3 points do not lie on a line, so if we have a rigid body, let's assume that this is our rigid body, and we have 3 different points, point A here, point B here, and point C here. If sum of all the moments at all of these 3 points is equal to 0, as it is mentioned in these 3 equations, these are also sufficient conditions for equilibrium. We will not prove how all of these conditions are equivalent, in the sense that if one of them is true, then all of them have to be true, but it's not very hard to prove them also. Okay, so now we move to the procedure for analysis. So anytime we so this is the procedure for analysis for a two-dimensional system. If we have a two-dimensional system which has a rigid body, and we want to solve for equilibrium, and we want to find the unknown forces, so first of all we would like to draw a free body diagram, and this is where all of our knowledge from previous chapter would come into handy about how to draw a free body diagram. A few important points here is that in drawing the free body diagram, anytime we have any supports connected to our rigid body, we would remove all of the supports, and we would represent all the supports with the corresponding reactive forces with unknown forces, as we have looked at in this lecture and the previous lecture. And we would also indicate all the dimensions of the body which are necessary for computing all the unknown forces. Okay, and once we have drawn the free body diagram, once we have labeled all of the known and the unknown forces, then we can apply the equations of equilibrium. Sum of all the forces in x are equal to 0, sum of all the forces in y are equal to 0, and sum of all the moments at any point O are equal to 0. Here again, because sum of all the moments we can choose any point O to compute our moments, so we would choose a point where the moments are simplest to compute. Okay, so once we solve some examples, we will see why sometimes we have a few points in our system where finding the moments is easier rather than at other points. Okay, so this is the first example for us to see today. We want to determine the horizontal and vertical components of reaction on the beam caused by the pin at B and the rocker at A, as shown in figure 5-12a. Neglect the weight of the beam. So this is, we have a beam here which has two supports. One support is at this point B, and this is a pin support, and the other support is at point A, and this is a rocker support, and we want to draw the free body diagram. Okay, so what were the steps for drawing the free body diagram? So first of all, let me just choose an axis. So our vertical axis is y and the horizontal axis is x. So first of all, again we first draw the beam itself, and first we draw all the known forces. So we have a force which is 200 newtons, which is acting downwards here, and we have a force which is D, which is acting at point D. Then we have a force which has an x component and a y component, and then these are all the known forces, so to speak. So let me just label all of them. So this force is 200 newtons, and this is 100 newtons, and this is 600 newtons, These are all the known forces, and now we want to replace all the supports by unknown forces. So this support A is a rocker, and as we saw that rocker provides a support which is vertical to the surface below. So this support would be vertically upwards. So we get one support reaction here, and this we can call as FA, because the point where the rocker is, the point of rocker is called A, and this B is a pin support. That means we would replace this with two forces, one force in the x direction and one in the y direction. Okay, and again we have to name these two forces. So this one I can call FBX, and this one I can call FBY. So this is the free body diagram. We have to label all the dimensions on the free body diagram. This is 3, this is again 2, and this angle is 45 degrees. So this completes the free body diagram. So this is the free body diagram for our system. The next step again is just to apply the equations of equilibrium, which means sum of all the forces in x are equal to 0, sum of all the forces in y are equal to 0, and sum of all the moments at any point O are equal to 0. So as we can choose any point to find the sum of all the moments, I would choose this point B to find the moments, because we have three forces which are acting at the point B. If we were to find the moments at B, all these forces would not have any moment, so the finding the moment would be the easiest. So first of all, sum of all the forces in x. So how many forces do we have in x? The first force is 600 divided by square root of 2, which is just the x component of this force, and we have a negative force which is minus FBX. That is our first equation. The second equation is for all the forces in y, which means FA minus 600 divided by square root of 2, that is this force, minus 100, that is this force, minus 200, that is this force, and then we have plus FBY. So we have these two equations, and the last equation again is just the moments equation, and that equates to, so the first moment would be because of this 100 Newton force, and this would be counterclockwise, so I am going to write it as positive. The second would be the force. Again you see that there is a 0.2 meter difference at the action of this force here. So the y component would produce a moment which would be equal to 600 divided by square root of 2 times 5, because the distance from here to here is 5 meters, and the x component also would have a moment which would be negative, and that would be equal to 600 divided by square root of 2 times 0.2. And the last term in the sum of all the moments is the term because of this FA, and again this would be now minus because this is producing a clockwise moment, so that is FA times 7 equals 0. So here we have the three equations of motion, and the only thing left to do now is to solve these three equations simultaneously to get the result. And the first equation is very simple. So from equation 1 we can already see that fbx is simply equal to 600 divided by square root of 2, and we can plug in the value of fbx in these two equations and solve them simultaneously. If we were to go through all of the math, we get that fby equals 405 newtons and fa turns out to be equal to 319 newtons. Okay, again this is simple simultaneous the solution for simultaneous equation, so I'm not going to go through all the steps about for finding these three unknowns. But I hope that the process is pretty clear. I've already attached the solution for this free body diagram example in my lecture slides also, so you can have a look. So this is it for today, and I will see you in the next lecture, inshallah.